So a buffer is a solution that is resistant to changes in pH. For example, if you just had regular water and you added hydrochloric acid, the pH would drop dramatically. But in a buffer, the pH would only drop a little. And so buffers are made by combining either a weak acid and its conjugate base, or a weak base and its conjugate acid. You can't use strong acids or strong bases. So, to see how buffers work, let's look at an example. So we have a solution with 0.5 molar of acetic acid and 0.5 molar of sodium acetate. So notice how we have a weak acid, acetic acid, and its conjugate base, as the acetate ion. So the major species in this solution will be acetic acid. Since it's weak, it does not dissociate very much. And then the sodium acetate is a soluble salt, so it will dissociate into its ions, Na plus and C2H3O2 minus, and then of course water. So the species that will control the pH of this solution is going to be acetic acid. So we write the dissociation equation for acetic acid, and then we do an ice chart. So we start with 0.5 molar of both acetic acid and acetate. Before, with acid and base problems, we just had some initial acid, but none of these guys. So in buffer problems, you have some of the acid and the reactant and product already present initially. So that's the main difference from the other acid-base problems. But otherwise, it's just the same. We do the ice chart, and then we plug those into the equilibrium expression, find x, and then that's just the concentration of H+, and from there we can find the pH. So the pH of this buffer solution is 4.74. So now let's look at what happens to the pH in this solution if we add 0.01 moles of sodium hydroxide. And we say that this buffer is 1 liter. So when we add sodium hydroxide, it'll dissociate into Na plus and OH minus. And we know that the hydroxide ion is a very, very strong base. So it's very attracted to protons. So it will find the best source of protons in the solution, which here is acetic acid. And then it will react with that acid to steal the protons. And since hydroxide is such a strong base, this reaction basically goes to completion. So you can see it's a single arrow, not a double arrow. So first we have to find out the final amounts of the species after this reaction takes place. So notice how this is not an equilibrium problem. This is just stoichiometry, since this reaction goes to completion instead of reaching equilibrium. So we can see that the hydroxide ion is going to be a limiting reactant, and they are all in a 1-to-1 ratio. So these guys lose 0.01 moles, while this guy gains 0.01 moles. So final amounts after the reaction, all the hydroxide is gone, acetic acid is 0.49 moles, and acetate ion is 0.51 moles. And also, be careful, you have to, since this is stoichiometry, we need to work in moles, not molarity. So before you start this, make sure to convert between the molarities that you got in the problem and the moles. However, in this problem, we just have 1 liter, and since at 1 liter, molarities and moles will be the same thing. So after you do this stoichiometry, you now do another equilibrium problem. So we added the sodium hydroxide, the hydroxide reacted to completion with acetic acid, and now that that's done, we do another ice problem with the dissociation of acetic acid with these new amounts after this other reaction with hydroxide. So new initial concentrations are 0.49 molar and 0.51 molar. Again, make sure you convert from moles to molarity. And then we just do the ice problem. So we find that the pH is going to be 4.76. So notice how even though we added a very strong base, sodium hydroxide, the pH of this buffer only increased by 0.02. So this is what a buffer does. It resists large changes in pH. So how does this work? So in order for a buffer to be effective, the amounts of the weak acid or base and its conjugate need to be much larger than the amounts of hydroxide or H plus being added. Notice in the last example, we had 0.5 moles of both acetic acid and acetate ion, and we only added 0.01 moles of hydroxide ion. So the amount of hydroxide that we added was much less than the amount of weak acid and conjugate that we had. So when any hydroxide ions or H plus ions are added, they are consumed in a complete reaction with either the weak acid base or its conjugate. So if H plus is added, it will react with the base to produce the weak acid. So in the previous example, we had acetic acid and acetate ion. So if we added H plus, then the H plus would react with the C2H3O2 minus to produce acetic acid. Now if we add hydroxide ion, it will react with the weak acid. It will steal the proton to produce water and the conjugate base, which is what happened in the example that we did.